In this discussion, we're going to look at conceptual and calculational aspects of solubility. Okay, first some terms, some you'll be familiar with, others maybe not. Miscible, we talked about this, meaning that they dissolve within each other. A saturated solution and unsaturated solution, we're going to get to those a little bit later. Here's a basic definition, but we're going to talk about those later. Solubility, that is the concentration of the solute in a saturated solution. Solubility is usually in units like grams per liter or sometimes grams per 100 grams of solvent. It can vary, but the key thing is that we're dealing with a saturated solution when we are measuring the solubility. Okay, so here let's look at how do we get a saturated solution. Well, we have the dissolving process begins. All right, and here our solute is green. So you can see as the more it dissolves, the greener our solvent becomes. And then as it dissolves, then we also have the reverse process happening. In other words, some of the solute molecules or ions that have come out into the solution will randomly hit the surface of the solid solute, and depending on their kinetic energy, they may just sort of go their own way, or they may be re-attracted into the crystal structure. And so we have a competing process. We have dissolving, and then we have the recrystallization that will occur. And so at some point, these two competing processes are occurring at the same rate. And so it looks like nothing is happening, but actually it's just that the two things are happening at equal rates. And so we don't see any change in the amount of solute that's in the bottom of our container. Okay, and so it would just sit there. Once it's saturated, no more solute, no additional solute will be added to the solution. Okay, typically increasing the temperature will increase the solubility of a solution or of a solute, meaning that increasing the temperature will allow us to dissolve more of the solute in the solvent. Some substances, decreasing the temperature has the effect of increasing the solubility, but just a few. And if the substance is one of the majority of them that will increase solubility as we increase the temperature, then we can create what is called a supersaturated solution, which means it's a solution that will hold more than the amount of solute that is in solution at saturation. And the effects that you can see of this, it's not a very stable condition, a supersaturated solution. And so as you can see in our picture here, is that if we've created this supersaturated solution, that anything that will start the crystallization process will usually cause it to occur fairly quickly. And so in this example here, here's our supersaturated solution. We put in our seed crystal, and crystals start to form on that. And then eventually we have our whole, all of our excess solute has recrystallized. Here's some solubility curves. As you can see here, we have, this one is grams of solute per 100 grams of water. It's a pretty common unit that you'll see on these solubility curves. And as you should also notice, the majority of them, to varying degrees, will increase solubility with an increase in temperature. However, we do have some substances, here's like the lithium sulfate, where we do have a negative slope on our solubility curve there. So it would not increase solubility as we increase temperature. In fact, it would decrease solubility as the temperature increases. Selective crystallization. This is a method that we use to separate contaminants from a substance. And we can do this when the substance is less soluble in the solvent than the contaminants are. So we can dissolve our mixture and then basically crystallize out the substance that we want and leave the impurities in the solution. Okay, gases are a little bit different than solids when they're dissolved in solution. Basically, most of them are going to be less soluble in liquids as we increase the temperature. You've seen this if you've ever had a glass of soda sitting out. As it gets warm, the carbon dioxide comes out of solution and your soda goes flat. Okay, we have a mathematical relationship that we call Henry's law. And here it's shown as the pressure of the gas is equal to Henry's law constant times the solubility of the gas. And one of the things to notice in here or to be aware of is that sometimes you will see this written with the Henry's law constant on the other side of the equation. So you may see it as K times the pressure of the gas is equal to the solubility. The key thing to remember is if you're working a problem and they're giving you the Henry's law constant, just look at the units that's on the constant and then you'll know which side of the equation that it needs to go on. Okay, so here's some curves showing you the decrease in solubility of gases based on temperature. Now, pressure and solubility. If you've ever opened a soda and you hear the gas escape, then you're probably aware of the fact that if we increase pressure over a solution that has a dissolved gas in it, then that increases the solubility of the gas. Decreasing pressure, the gas will come out of solution, just like the carbon dioxide when you pop the cap on a can of soda. So this is showing you here kind of a relationship here. And the key thing to remember here is the fact that if you look at this, high partial pressure, the pressure above the solution that we're referring to is the pressure from particles of the same gas that is dissolved in the solution. So if we're talking about applying a pressure, say in the vapor space in a can of soda, to keep the carbon dioxide in the solution, then that vapor space is going to have carbon dioxide in it. It has to have the same gas applying the pressure above the solution as the one that we want to keep dissolved in the solution. And so here you can see we have a real nice linear relationship between gas pressure and solubility in water, which is what you would expect given the fact that Henry's law gives us a linear relationship. Here it's telling us that there are some, or gives us two common examples that would not follow Henry's law. Hydrogen chloride and carbon dioxide, it says, would not follow Henry's law. And the basic reason is that they are going to actually interact with the water. So we've got some additional factors at play there. All right, so let's look at an example problem here. All right, here we have the solubility of methane in water at 1 atmosphere of pressure is, it says we have a pressure of our gas when it's 1 atmosphere, and our temperature is 20 degrees Celsius, then our solubility is 0.025 grams per liter. And it says it wants to know what will the solubility be if the pressure is 1.4 atmospheres and our temperature is 20 degrees Celsius. Okay, if our temperatures are the same, then the temperatures are the same, the gas is the same, then our Henry's law constant will be the same. And so we can, and here we can choose whichever form we want to use. So let's just use the one that was on the slide. Okay, and so if I put in 1 atmosphere and I have 0.025 grams per liter, then that tells me that I have a Henry's law constant of 1 divided by 40. Okay, and let's see, my units on that are going to be atmosphere liters per gram. Okay, and so if I come over here, again, I'm going to use Henry's law. And so my pressure is 1.4 atmospheres, and I have 40 atmosphere liters per gram times my solubility. So 1.4 divided by 40 gives me a solubility of 0.035 grams per liter.